All right, part 4, graphs of relations and functions. We can represent the function that associates every whole number with its double in several ways. We can use a table of values. Okay, so the whole number x and then double the number, we'll call that y. So if we start with 0, double 0 is 0. If we start with 1, double 1 is 2. If we start with 2, double 2 is 4. If we start with 3, double 3 is 6. If we start with 4, double 4 is 8. Okay, so the table continues for all whole numbers. Okay, so the domain is the set of whole numbers. Okay, now the range is the set of even whole numbers. Now the reason why they're even is because they're always twice whatever the domain is. Okay, and then 2 times an even number is an even number, 2 times an odd number is an even number. So basically this double column will always be divisible by 2, which is of course the definition of an even number. Okay, awesome. So we know the relation y equals 2x is a function because each value of x associates with exactly one value of y, and each ordered pair has a different first element. Okay, so the domain, these are all different, okay, than the doubles. Okay, now if you have a look at the graph, y equals 2x, see there's all these points here. Now, the domain of the function is the set of values of the independent variable. For the graph above, the domain is the x values. So the domain is all these values, domain. Okay, the range then is all the y values. Okay, so the dependent variable for the graph above, the range is the y values, awesome. Okay, when the domain is restricted to a set of discrete values, the points on the graph are not connected. Okay, so let's talk about this whole discrete versus continuous thing. Discrete data is such that only certain values are allowed. Okay, so the points on the graph are not joined. So an example of this, so the number of coins, the number of tickets, basically anything that you can't split into smaller chunks. See, up in this graph here, we said that the domain, the x's, were all the whole numbers. So if I was to join these dots, okay, that means that every middle value is allowed. Well, that means that I can have an x value right there. Well, right there is like 0.3. Now, is 0.3 a whole number? Well, it isn't. Okay, so the thing is, this data is discrete because we're not allowed to have all those middle points. Okay, great. Continuous data, on the other hand, is such that all values in the domain are allowed, so the points on the graph are joined. So examples of these is time, mass, distance, okay, basically anything that can be split into smaller chunks, right? It makes sense to have 1 second or 1.1 second or 1.01 seconds. Okay, so if we have time, so time on the bottom, okay, then all of these points would be allowed because I can be 1 second, I can be 2 seconds, I can be 1.5 or 1.25. So I can be all those little points in between so I can connect the dots. Okay, awesome. All right. Now, a relation that is not a function has 2 or more ordered pairs with the same first coordinate. Okay, we've talked about this. Okay, so when the ordered pairs of a relation are plotted on a grid, a vertical line can be drawn to pass through more than one point. Okay, now I know on your page the black and white doesn't show up all that well, but the color does pretty good. Here, let me just draw in red so you can see this better. I know it's not the same shade, but here you have these points. So these are the points in the function or in the relation. Okay, now if you look, these 3 points here will all have the same x coordinate. So this is the point 1, 3. This is the point 1, 4, and this is the point 1, 5. Now, as soon as you have the same x coordinates, it's no longer a function. So So how that shows up on a graph is these show up in a vertical line. Okay, so you can draw a vertical line through more than one point. So this is not a function. Okay, so a function has ordered pairs. So I'm reading up here now, guys. So a function has ordered pairs with different first coordinates. So when the ordered pairs are plotted on a grid, any vertical line drawn will pass through no more than 1 point. So if I draw a line here, 1 point, 1 point, 1 point, 1 point there, 1 point here, 1 point there. Okay, so this is a function. All right, so this brings us to the vertical line test for a function. A graph represents a function when no 2 points on the graph lie on the same vertical line. So you can place a ruler vertically on the graph and then slide the ruler across the graph. If one edge of the ruler always intersects the graph at no more than 1 point, it represents a function. If the ruler touches more than 1 point at any place on the graph, then the graph is called a relation. Okay, so we have graphs of functions, graphs of relations. This first one here, okay, this is called a relation. This one is called a function. Okay, awesome. Okay, so example number 1. Okay, identify whether a graph represents a function. So which of these graphs represent a function? Justify the answer. So if you look at A, if we draw vertical lines through all those points, we only touch 1 point ever. So this one, A, represents a function. And that's because it passed the vertical line test. So vertical line test, the VLT. Okay, so if we look at B, masses of students against height, oh, look at this. There's 2 points there. Oh, there's 2 points here. Well, really, only to be not a function, you only have to cross 2 points once, but this particular graph crosses 2 points 3 separate times, so this is not a function. So not a function, and yeah, pretty crazy. So, and it did not pass. So it failed or did not pass the vertical line test. Okay. So often when dealing with graphs and functions, we are asked to find the domain and range of a function. Okay, on a graph, the domain is the set of all horizontal values, typically x, but we're not stuck on x. We don't have to be x values. The range then is the set of all vertical values, so typically y values. Okay, there are 2 different methods for describing domain and range. Okay, they're called set builder notation and interval notation. You are responsible for both. Okay, the textbook uses set builder quite a bit, but like I said, you have to know both, so I'm going to show you both. Okay, you have seen part of set builder before. Set builder uses the greater than or less than, greater than or equal to, less than or equal to signs to specify the values that the horizontal and vertical values are in between. Okay, interval notation, on the other hand, makes use of either square brackets or circle brackets to identify the beginning and end points of the horizontal and vertical values. The square brackets indicate that the interval is closed, which then includes the final number. Okay, the circular brackets indicate the interval is open, which does not include the final number. Okay, we're going to make this clear in the examples. So, okay, moving on. Okay, so for example, on a graph, if the x values are between 0 and 5, and the y values are between -3 and 5, then we can write. So in set builder notation, and I know this is kind of fancy, but you'll get used to it. So the domain, okay, so you're going to have, so the domain is the set, so that's the curly brackets. So the domain is the set of all x's such that, so that little line is the abbreviation for such that. Okay, so now our x is in between 0 and 5. So look at this. If we go 0 and 5, let's just put the x in between them. Okay, and I am bigger than or equal to 0, but smaller than or equal to 5. So we go 0. So 0 is less than or equal to x, and x is less than or equal to 5. Okay, then we have a comma, and we say that x is an element of the reals. So it's all the real numbers. It's a continuous, all the numbers in between 0 and 5. Okay, and then we end with our curly bracket again. Okay, in interval notation, how that looks is the closed bracket says that we can equal 0. Okay, so we start at 0 and go up to 5. Okay, and we can equal 5, so again it's a square bracket. So we would say the domain, okay, is from 0 to 5. Okay, awesome. We do the range in very much the same way. Okay, so if the range is between -3 and +5, we just put the y in between the -3 and the 5. Okay, and then we are bigger than, or the y value is bigger than or equal to -3, but less than or equal to 5. Now, if you go in order with the small one, the small boundary on the left and the large boundary on the right, the signs will always end up pointing that direction. Okay, so it's just a helpful little thing. Okay, and then of course we write range. Okay, so then the curly brackets y such that, so that line is such that. Okay, so -3 is less than or equal to y, which is less than or equal to 5. Y is an element of the real, so it's any number in between -3 and 5. It's continuous data as opposed to discrete. Okay, so that's how we write the range. And then in interval notation, again, we can equal -3. That's why it's a square bracket. And we go all the way up to +5, and we can equal +5, so it is a square bracket again. So what does this look like on a number line? For the domain, okay, we go from 0 all the way up to 5. Okay, and I can equal 0, so we have a closed dot. I can equal 5, so I have a closed dot, and we just have every number in between. Okay, so we go from 0 to 5, every number in between. It's awesome. Okay, for the range, we go from -3, -2, -1, 0, 1, 2, 3, 4, 5. So 0 up to 5. Okay, I can equal -3, I can equal +5, and I am every number in between. Okay, so that's perfect. Okay, so we also have situations when a graph or a function continues on in one or both directions. For instance, if a graph starts at -3, 2 and goes down forever and right forever, we would write this. Okay, so let's see, -3 is here, +2 is up here. And we've told you that it goes down forever and right forever, so it's kind of like this. All right, so the domain here, so again, we write the word domain. Okay, you can simplify that to a D a little later on, but for now, let's just write it out proper. So the domain, okay, so swirly brackets or curly brackets, x such that. Now, x is bigger than -3, but it goes all the way up to infinity. So really, we just say that x is bigger than or equal to -3. Okay, that's awesome. Now, once we have that, we are all the numbers, as long as we're bigger than -3. So it's continuous, so we say x is an element of the reals, and close our swirly brackets. Perfect. Done. Awesome. Okay, the range, on the other hand, okay, so range is the y coordinates, so it's y such that. Now, this time, it's going down, so that means all the y values are smaller than +2. So y, and then how we write that is smaller than or equal to +2. So y is less than or equal to +2. Okay, and then it's continuous data, so y is an element of the reals. Okay, so there you have the range. Okay, so again, in set builder notation, that's the domain, that's the range. Okay, awesome. Now, in interval notation, though, okay, so the domain, it starts at -3, so we have a square bracket at -3, but it goes all the way up to infinity. Now, the funny thing about infinity is you can never equal infinity, so we have a circle bracket there. Okay, so that means that you can get close to infinity, but you can never actually get to infinity. Okay, and then of course the range is the other way around. It goes all the way down to negative infinity, right? The y values will go all the way down, okay, to negative infinity, but it stops at +2, right? The y values stop at +2, and we can equal +2, so then we have a square bracket. So what does this look like on a number line? Okay, so the domain, so x is bigger than or equal to -3. So if we have -3, so we can equal -3, so we have a closed dot, and we are bigger than -3. So we go all the way up to infinity. So that's what that looks like on the number line. Okay, the range, on the other hand, so for the number line for the range, okay, we start at +2, so 0, 1, 2, so +2, and we go down to negative infinity. So that's what we look like on the number line. Perfect. Okay, no, this one's a little long, so if you need to press pause at any time, go have a break. You know, that's not a big deal. But this domain and range bit, it is tricky, and it's kind of important. So we're taking it slow, one at a time, lots of examples. Okay. All right, one last scenario involves an open circle on the end of the graph. This denotes that the line goes up to, but does not include that particular number. Now, I think you learned this in grade 9, but we're just kind of recapping. Okay, this would use either the less than or greater than sign, okay, or the open brackets for interval notation. Okay, this is called an open interval. Okay, so consider the statement, children 3 or older, but younger than 12. So this means that children can be 3, but they can't be 12. They have to be younger than 12. Okay, in set builder, okay, you are allowed to equal 3, so that's why we have the less than or equal to sign. Okay, so 3 is less than or equal to x. However, we're not allowed to be 12. Like, you can be 11 years and 364 days old. Okay, but as soon as you get to 365, that means you're now 12, and it's not allowed. Okay, so you cannot equal 12. Okay, and that's denoted by just the less than sign. There's no equal there underneath. So in interval notation, okay, so you're allowed to equal -3, so square bracket, but then you have an open interval on the 12. You're not allowed to equal 12. Again, 11.9999999 is just fine. 12, no. So what does this look like on a number line? Okay, so from 3 to 12, so 3 is here. Let's put 12 there. So I have a closed dot saying that I can equal 3, but we put an open circle around the 12. Okay, so that means that you can get up to 12, but not include 12. Okay, so that's what that looks like. So a summary for this, the following table shows set builder and interval notations along with a number line for an interval from 1 to 2. Okay, so in set builder notation, so if I include 1, I am bigger than or equal to 1, greater than or equal to. If I don't include 1, okay, I'm just greater than 1, no equal sign. Okay, if I don't include 2, I am less than 2. If I do include 2, I'm less than or equal to 2. Okay, interval notation, if you have that equal sign there, then it's a square bracket. If it's not equal to 1, then it's an open or circle bracket. Okay, less than, again, is the circle bracket. Less than or equal to is the square bracket. Okay, and then on a number line, equal to has the closed circle. not equal to has the open circle. Okay, so that's a nice little summary for us. Okay, so let's try some more examples of this. Okay, determine the domain and range of the graph of the function. Okay, use both set builder and interval notations. Okay, so in this one, see how there's a closed dot right there? Okay, so that means the graph stops. See, there's no dot on the end of this. Usually we use arrows to show this, but if there's no dot, it just keeps going forever. Okay, that's what we have to do. Now, the domain, and I said we could abbreviate that with a D. So the domain, swirly brackets, so x such that. Now, the x's here, they go all the way down to negative infinity. So look, we start at positive 5, and we go all the way that way. We'll touch all those x's. Okay, so x is less than or equal to positive 5. Okay, once we're there, we can be all the numbers in between, so x is an element of the reals. Okay, usually this gets shortened to domain is x is less than or equal to 5. Okay, that's usually how it gets shortened to, but you still need to at least recognize the long version. Okay, so the range, on the other hand, is the set of all y values. Now look, the y values are going to go all the way down to negative infinity and all the way up to positive 2. Okay, at positive 2, it doesn't go any higher. Okay, so the y values, they're always going to be less than negative 2. So y is less than or equal, to positive 2. I think I said negative. Okay, positive 2. Okay, and then y is an element of the reals. Awesome. Okay, that sometimes gets abbreviated to x is less than or equal to 2. Okay, and that's the domain and range. Okay, that's also set builder. Okay, so for interval notation, I should have drawn a little smaller. Sorry, guys. Okay, so for interval notation, it goes all the way down to negative infinity and then all the way up to 5. And I can equal 5, so we're good. We can never equal negative infinity, so that's why it's a circle bracket. Okay, for the range, again, we go all the way down to negative infinity and all the way up to positive 2. We can equal positive 2, so square bracket. Awesome. So that's A. So let's try B. I'm going to have to write a little bit smaller because I just don't have enough room. Okay, so the domain is, so that's all the x's. So the x's go from negative 3 up to positive 5. So negative 3 to positive 5, we put the x in the middle. Okay, so the domain, swirly bracket, x such that, so negative 3 is less than or equal to x, which is less than or equal to 5. Okay, once we're there, it's all the values in between, so x is an element of the reals. Okay, that's awesome. In interval notation, that's square brackets, negative 3 to positive 5. Okay, so that, of course, is the domain. Now, the range, on the other hand, is y such that, so the y values, they go from positive 3 up to positive 7. So 3 to y to positive 7, and they're all the values in between, so it's continuous, so y is an element of the reals. Great. Okay, so the range in interval notation, okay, we go from 3 up to 7 and square brackets for both. Okay, so that is how we do those ones. Okay, couple more, guys. Again, if you're getting tired and bored, press pause, walk around for a bit. I'm sorry this one is so long, but there was a lot to teach you in this one. Okay, so example 3a. Determine the domain and range of a graph of a situation. So the graph shows the number of fishing boats, N, anchored in an inlet on the Queen Charlotte Islands as a function of time. Identify the dependent variable and the independent variable. So the dependent variable is time. And the number of boats is the dependent. Independent is time, dependent is the boats. Now the number of boats depends on the time. So the number of boats is the dependent, the independent is time. Okay, so why are the points on the graph not connected? Well, you can't have half a boat. Have half a boat. So if I connected these dots, now it makes sense to have time connected. Okay, but if we do this, look, that means that I can have, so this would be 14 boats. So this would be 13. Well, this number right here, that would be 12 and a half boats. Okay, well, you can't do that. So these have to be discrete values. Okay? Again, can't have half a boat. Okay, and then determine the domain and range of the graph using both notations. So the domain here, the domain for dots is a little trickier. Okay, because the thing is, we don't necessarily have all the points. Okay, but it looks like we go from 9, okay, 10, 11, 12, 1 o'clock would be 1300, 2 o'clock, 3 o'clock, 4 o'clock. So that's as far high as we go, from 9 o'clock to 4 o'clock, or 0900 up to 13, 14, 15, 1600 hours. Okay, so the domain is, so swirly bracket, time such that, okay, we have 900 hours, so 9 o'clock, or 0900, I guess they're saying, okay, is less than or equal to time, which is less than or equal to 1600 hours. Okay, now, how do I signify dots? Okay, well, that one is time is an element of the integers. Okay, now, really, I guess because it's from 9 to 17, we can also say those are natural numbers. Integers are positives and negatives, and I guess you can't have negative time. So, time is an element of the natural numbers. Okay, so at least in this case. Okay, the range, on the other hand, okay, that's the number of boats. Okay, so if we say, because that's the n, so it's n such that, so how many boats do I have? Okay, so we had, let's see, 6 boats there. Okay, so we have a minimum of 6 and a maximum, okay, that's 25 boats. Okay, now, the problem with this, okay, is again, it's dots, but that's okay, it's okay. So we have a minimum of 6 boats. That's less than the boats, which is less than or equal to 25. Okay, and then of course the n is an element of the natural numbers again. Okay, because I can't have less than 0 boats, and we can go up as well. For the context of this question, I'm from 6 to 25. So that is my range. Okay, in interval notation, the domain, so I can equal 9 o'clock, so 0900. Okay, and I can equal 1600 hours. The range, okay, I can have 6 boats in the harbor all the way up to 25. And because those numbers are included, I use these square brackets. Okay, so that is both notations for that one. Okay, so let's try another one. Okay, so determine the domain and range of a graph again. Okay, this graph shows the approximate height of the tide, h meters, as a function of time at Port Clemens on June 17th of 2009. Okay, again, identify your variables. Okay, so if you look, we have height and time, and the dependent variable always goes on the vertical, so the height depends on the time. So height depends on time. So time is the independent variable and the height is the dependent variable. Okay, perfect. Okay, so why are the points connected? Well, the points are connected because we can have, at any given time, we are going to be at a certain height, and I can split time into smaller portions. I can split height into smaller and smaller portions. So this point right here, what would that even be? So 10 o'clock, 11, 12, 1. So these are hour spaces. So this would be about a half an hour. So at half an hour, I can be at that particular height. And that's actually allowed. So that's like 1.1 meters-ish. That exists, that actually happens, so we can connect our dots. It's continuous data. So time and distance are both continuous. Okay, that means all the middle values are allowed. Okay, and then determine the domain and range. Okay, so the domain, so we have x such that, well, it's not an x, sorry, pardon me, it's a time. So the domain is time such that, so we go start at 900 hours, so 900 hours, time, and then we are less than, okay, 13, 14, 15, 1600 hours again. 1600. Now this time, the time is an element of the reals. Okay, so time can be anything along there. Okay, the range, okay, is the height. Okay, and that measures from, okay, so let's see, each one of these is 0.2 of a meter, so that's 0.1, so that's 0.9 meters. 9 meters is where we start. Okay, we don't need the units on there, sorry. So 0.90 meters. Okay, and then we go up to, it looks like 1.5 meters. Okay, so height, and that's less than or equal to 1.5 meters. Okay, and then the distance is also an element of the reals because those heights can be anything in between as well. Okay, in interval notation, okay, I can equal 900 hours, so square bracket, and I can equal 1600 hours, so square bracket again. For the range, I can equal 0.90 meters, so square bracket, and I can equal 1.5 meters, so square bracket. Okay, so that is that domain and range in both of those notations. Okay, and then last one, everybody. I know this has been a long one. I'm sorry. Okay, example 4, determining the domain values and range values from the graph of a function. So here's the graph of g of x equals 4x minus 3. Now remember, g of x is just y, so y equals 4x minus 3. It's the same thing. Okay, determine the range value when the domain value is 3. Okay, so when the domain value is 3, what's the range value? What's the y value? So we just look on the graph. So look, the x value is 1, 2, 3. So here, okay, so that's the range value. So look, if we scroll that across, so look, each of these ticks is 2, so that's 10. So the range value, when the domain is 3, the range, it looks like it's 9. Okay? Now determine the domain value when the range value is -7. So when y is -7, so let's see, -2, -4, -6. So -7 is about here. Okay, so if -7's there, so we just track up to get the domain value or the x value. Okay, and that is -1. Perfect. Okay, so that's it for domain and range. I know this was a long one. This is a hard section, and it's not so, pardon me, it's not that it's hard. It's just, it's important. We do a lot of domain and range for functions later on and in Math 20 and 30, so it's just a big deal. So anyways, I need you to practice this section. It's section 5.5 in your textbook, starting on page 294. So you can either use your textbook or print the work pages from the workspace card. Then you can write all over them, of course. I keep saying that, but I'm going to keep doing it. It's fine. Okay, and please do all these questions. Remember, you can always do more. Make sure you show your teacher at the end of that so they can keep tabs on your progress. And good luck. I will see you next section. Thanks.